Okay, thank you. Hi everyone. Welcome to the weekly TCS seminar at the Jagiellonian. Today our speaker is Vida Dujmović from University of Ottawa. Vida finished her degree at McGill, master degree and PhD degree. But before you started your studies in Zagreb, right?
Zagreb, yes.
And well, I know Vida. I think Vida is known for her work on graph layouts, specifically stack layouts and queue layouts. That is the subject of the talk today. My perspective is that usually it connects with the structural side of the graph theory. So often we see relations to tree decompositions, tree width, and so on. But I also see some connections over the way to graph drawing, right? Yes. So thank you, Vida, for joining us. Thank you for accepting the invitation, and we are ready whenever you're ready.
Yes. Oh, share screen. Yes, that's what I was looking for. Or should I do share? Let's see if this is working. Can you see the screen?
Yes.
Okay. So thank you for inviting me. It's a pleasure to speak in your seminar, even though it's online. So let me try to, do view. Where is this thing? Where's full screen? Oh, there you go. Enter slideshow. Okay, so today I will talk about, it's almost like a survey talk of what we learned in the last 10, 20, 30 years, various members of graph drawing, graph theory, computational geometry. Why is this moving on its own? Okay, pause. All right, let's try community. So I'll try to give you an idea what we learned and what we still don't know, what's an interesting open problem in the area. So let me start by asking you to imagine, I give you any graph and I ask you to put vertices on a line in any order if you like. And then we look at two edges. Okay, so this is really not a line because I added these yellow, but if there was space, imagine that these yellow dots are actually on the same line as the top. So I ask you, okay, place the vertices on a line. And now let's look at the relationship that two edges can be in. There are basically three relationships that combinatorially that edges can be in. And here's the first one, where if you, by relationship, I mean, you look at the endpoints of these two edges. So in this first example, you will have, if you have edge E1 and E2, you will have first endpoint of E1, then of E2, then again E1 and E2. And if you imagine these two edges drawn as an arc in a half plane, because I said put vertices on a line, these two arcs would be crossing. So we say that the relationship of these two edges in the ordering is that they are crossing. If the endpoints come in this order, so if this is E1, the top one, and the bottom one is E2, then if the endpoint come in order E1 and then both endpoints of E2 and then only E1, in that case, if you imagine edges being drawn as arcs, you would have one edge drawn inside of another without crossing, and we say that these two edges are nesting. It's based on the picture, it's clear why. And finally, if you have endpoints on E1 both of them come completely before any other endpoint of E2, these two edges are disjoint. So these are basically the only three type of relationships two edges can you have in any given ordering of the vertices. So there have been studies where you say, what type of graph can I have if you're not allowing two edges to cross? So think of a question, I want to order the vertices of a graph and then in such a way that no two edges are crossing. Which graphs admit such layout? And it's graphs like this. They are basically outer planar graphs. Why? We have all the vertices on the outer face. We can draw all the edges on one side such that they're not crossing. So that's basically a definition of an outer planar graphs. So a graph, if you like, you can imagine closing these two ends, and you end up with a drawing where vertices lie on a cycle, and inside you don't have edge crossing. So if you look at a set of, if you have a vertex ordering and a set of edges such that no pair of them cross, we call that a stack for various reasons. So it's a set of non-crossing edges. Okay, what about if, so this is if you forbid crossings. What about if you forbid nesting of the edges? What kind of graph can you have? You want to find an ordering such that no two edges nest. So what kind of graph has such an ordering? It turns out, okay, so here's an example of a drawing. No two edges of this graph cross, no two edges of this graph nest. It turns out these graphs are also subgraphs of planar graphs. I'm going to get to that later. So definition of a Q is a linear ordering of vertices and edges are such that no two of them are nested. And the definition of stack is that no two of them are crossing. Okay, so not all of all the graphs have a stack layout like that, or a Q layout like that, such that no two edges nest or no two edges cross. So the definition can be extended to all graphs as follows. So we say that a stack number of the graph is you find an ordering of vertices such that, and then you also find a coloring of the edges with the smallest possible number of colors, such that if you look at only at the edges that are colored the same colors, among them you don't have two edges that cross. Okay, if you have that, and if you have say k edge colors, then we are talking about a graph that has a stack number k. In other words, if we look at a family of graphs, we say that the family of graphs has a stack number k if every member of the family has a stack layout with that can be colored with k colors, such that each color class doesn't have crossings. Okay, basically these color classes are often called pages. This notion of stack layouts or stack number has been introduced before in many contexts, and depending which page per you find it, you're going to find stack number as called also a page number or book thickness, depending on which paper you find it. So Q number is defined similarly, except that now among the edges that are colored with the same colors, you don't allow two edges of the same color to nest. So to repeat the Q number of the graph, you want to find an ordering and the coloring of the edges in the minimum number of colors, such that each color class induces a Q. In other words, no pair of edges of the same color are nested. Okay, so these two quantities, by the way, even this was studied. So we are saying here, we are looking at the layouts where you exclude crossings. You're looking at the layouts where you exclude nesting. You may ask, what about this third relationship? What about if you exclude edges that are disjoint? What type of graphs you can have? We studied that. It turned out it's not so interesting, actually. It turns out to be fairly related to chromatic number. The graphs can be super dense and have this disjoint number, if you like, a constant. So it's not a very interesting property, nor did it have any application. And these ones stacks, and well, other than the chromatic number, if you like. But these one stacks and Qs actually appeared in various applications over the years, from graph layouts to computational complexity. In fact, I will mention maybe that, but just so you know, I'm not going to go into depth into any of these, just so you know that these are not completely artificial notions, that they come naturally in a number of applications. So this talk will be about stack number, a Q number of the graph, and the relationship between the two, and what we've learned over the years. So here's the main question that we want to attack. Which of these two notions is more powerful, a stack number or a Q number? What do I mean by that? So for example, I can say that the Q number I would consider Q number to be more powerful if than the stack number. If whenever stack number is constant, then a Q number is constant too. But in addition, there are graph families for which Q number is constant, but stack number is not. Okay, so in that case, I would consider Qs to be more powerful than stacks. So again, to be more specific, we would say, well, it's exactly what I said. Whenever stack number is constant, I want to prove that the Q number is constant. But on the other hand, there is a family for which Q number is a constant, but stack number unbounded. In that case, I would say that Qs are more powerful. I can do with Qs always as well as with stacks. That's loosely what it's trying to say. And of course, you can define the same thing in the other way, where you're replacing all of these Qs with stacks and stacks with Qs in this definition. So this was actually asked a long time ago, in 90s. Doesn't feel that long to me, but it was a long time ago. At the beginning of the 90s, this was asked by Heath, Latenberg, and Rosberg in their paper. This question was asked specifically, which is more powerful, stacks or Qs? Sorry, the phone is ringing. So in other words, if you look at this definition, and let's say the answer is no for one of them, it would imply that there are families for which Q number is bounded, but stack number is not, or that there are families for which stack number is bounded, but a Q number is not. So in other words, they would be families of graphs that separate these two parameters, okay? And we didn't know any such families. So in fact, but before I go into what exactly we knew, let me give you, because I threw these definitions of you. If you've seen them before, many of you have, they are natural, but if you haven't and you never thought about it, let's look at some graph family and how you would define a stack layout or a Q layout. Let's try to be something simple. What about trees? Okay, how would you find a stack layout with, let's say, one stack, or Q layout with one queue of trees? Is that possible? In fact, it is. And the way to do this, you look at this top picture here. You start with a drawing of the tree where you think it's rooted. You put a root, let's say, on one line. And then on another parallel line, you put two of its children. Then on another parallel line, line 3 here, you put the grandchildren, and so on, in such a way that there is no crossing. So you kind of draw it in a natural breadth first search way. You draw a tree. So from this drawing, you can get both Q layout and stack layout. And here's how. So basically for the Q layout, you just put vertices. Well, remember, to find a Q layout, you need first vertex ordering and then edge coloring. That satisfies the property that we want. In case of Q layout, no two edges are nested. So if you look at this tree here, what you want is that you order. How do you find ordering? You put vertices from the first line first, from the second line first, from the third line, and so on. And one other decision you have to make, in which order on the line the vertices appear. And in here, these arrows tell you that, basically from left to right. So you put these lines, you spend a couple of seconds on that, and you realize that if you do that, you won't have any two edges crossing in this drawing of a tree. You can do something similar for stacks. So now you don't want crossings. All right, but I mean, here there's gazillion crossings, so sure, clearly we shouldn't do what we did here. But you can still put vertices of line 1 first, then line 2, line 3, line 4. But then when you think about in which order the vertices in the line should be in the layout, you alternate. If you used left to right for line 1, then you're going to use right to left for line 2, then again left to right, and again right to left. And you think, if you think of it geometrically, if you put vertices on the first line here, And then on the second line, you can imagine that you're inverting the line and you're not going to create the crossings between these two lines. So if you are inverting that, you will get, so these green edges would be edges between line 2 and line 3. So you're going to end up with, you can color the edges with 2 colors. I draw 1 color below such that monochromatic edges don't cross. In fact, you can do better for trees. You can do 1 stack. But I just wanted to show you this layering strategy because this appears throughout this talk and through so many of the things that we learn both in stack layouts and queue layouts. And let's look at, okay, so here's an example of a queue layout of a tree, nicer pictures. All these electronic ones were done by David. But here's a small tool that we've just seen. And this was crucial for everything, including some breakthrough results we had together with Piotr and Torsten a number of years ago. It's a trivial tool, but it's super powerful. And here's what he said. If you have, if you look at a bipartite graph, and if you draw vertices on one bipartition on one line and vertices of other bipartition of another in another line, and in between you have straight line non-crossing drawing of edges between these two bipartitions. Imagine you have that. Somebody gives you that. I tell you this graph that I drew, no matter how you draw it, such that there are no edge crosses in between, it's trivial to make this graph either into 1 stack layout or 1 queue layout. So we actually just saw how to do it. If you want 1 queue layout, you put vertices on layer 1, then vertices of line 2 or layer 2. In the order, in both cases, order left to right, and you get a queue. If you invert one order, like here, so left to right top line, right to left, the bottom line, you're going to get a queue. You're going to get a stack, like on the right-hand side. And more generally, so here you have that these red edges are non-crossing. If you had K color classes in between these two lines, so if you had edges that are colored with K colors and each color class is non-crossing, if you do this trick, you put 2 lines one after another, you're either going to get a K stack layout or K queue layout. So I call this a small tool, and this appears in many ways, you'll see. Okay, so this small tool already tells you, for example, what is the stack layout or queue layout of a grid? Okay, so can you do this constant number, or maybe that's something that is unbounded? It turns out it's really not, because grid, a drawing of a grid is exactly like this. And one obvious way to do it is to draw the line parallel going through these blue edges, drawing 2 horizontal edges. And in between 2 lines, you have a non-crossing red graph. So if you want a queue layout, you just draw lines in this order, and the red edges are going to form a queue, and the blue horizontal edges form a queue. Nothing is crossing, and you get a 2 queue layout. But in fact, the little tool gives you that a queue layout of a grid is actually 1. It's just you pick different lines from horizontal or vertical lines of the grid. If you pick your parallel lines to be like this, so these are your parallel lines. Now look at what you have between any 2 of these lines. Between any 2 of these lines, you have a non-crossing blue graph. And that's exactly what a little tool requires. You have a bipartite graph in between non-crossing things. So if you layer these lines one after another, you keep left to right order, you're going to get 1 queue layout of a grid. Okay, so these are the only little examples I'm going to give you. But let's find out what was known before. Remember, we are trying to see, can we separate stacks and queues? Okay, so if we can separate stacks and queue, there should be a family of graphs for which stack number is constant, but queue number is not, or the other way around. Well, as I already showed you, a graph has in paper from 1979, it was already known that graph that has a stack layout 1, they're basically autoplanar graph. The definition is the same. The 1 queue graphs are basically characterized. They are planar and they look a little bit like a grid. I'm not going to go into that. Also, 2 stack graphs are Hamiltonian because remember you are drawing vertices on a line And if you're using two stacks, you can add all the edges on the line and make a graph Hamiltonian without introducing extra crossing. So there are subgraphs of Hamiltonian graphs, two stack graphs. Okay. Another thing we know about these two notion is that graphs that have a constant stack and Q layouts have linear number of edges. Therefore, if you want unbounded stack number or Q number, well, as long if you have more than linear, if you have a omega of n edges, then your both stack and Q number are unbounded. So that's not separating us. In fact, there are even expanders of so-called monotone bipartite expanders that have a constant Q number. This is actually an amazing result. What are these monotone bipartite expanders? Are basically these guys. So these 2 or 3 people, I forgot their names. What they showed is that you can have an expander that looks like this. So basically a bipartite graph where in between the two bipartition, you have a constant number of non-crossing matchings. Okay, so, and that graph is actually, and you have such graphs that are expanders, and based on the little tool, they have a constant Q number and constant stack number, because each non-crossing matching is, well, that's the only thing that we required here for a small tool to work. Okay, so these O1 constant monotone bipartite expander are not a class that separates the two. They both give us a bounded stack number and Q number. Okay, so let's see what we knew. So before this work that we did in 2019 that I will mention briefly, we knew actually much more about stack numbers than Q numbers. For example, we knew that stack number is bounded from bounded three-width graph for all planar graphs, for all bounded genus graphs, for all proper minor closed families. And if you subdivide edges of any graph enough, you get a graph eventually that has a constant stack number. So we knew that for stack number. For Q number, we knew much less. In fact, it was conjectured in 92 that tree trees, in fact, planar tree trees have bounded Q number, unbounded Q number. So if that were true, that would have separated stack numbers and Q number, because, you know, we knew that stack numbers have bounded, bounded three-width graphs have bounded stack number. But it turns out that that is not true, that bounded three-width graphs have in fact bounded Q number. So that was not the class of graph that separates them. And then if you look down this list, the next one is planar graphs. Well, stack number of planar graphs was known to be bounded by a constant 4. And if you go down the list, you think, what about planar graphs? Maybe planar graphs separate these two notions. And this question was asked again in 92, and it has been open for until 2019. How is that? Almost 20 years? No, a little more than 20 years. I'm bad with this. Anyways, can't do math when people are listening to me. Anyways, for many years, the problem was open. And in a workshop in Barbados in 2019, we finally cracked this problem. And it turns out that many of the tools were already there. You have to put them together. In some ways they were there, in other ways they were really not there. But anyways, the little tool was one of the tools used. So here's the main result that turns out to be super useful, way more useful than any of these stack and Q layouts. So here's what we showed. This group of authors here on the top, we showed that every planar graph is a subgraph of a strong product of two graphs, where one is a path, P stands for a path, and one is a graph which has a constant tree width. Originally, we had an 8. I think the best right now is 6. Correct me if I'm wrong. I think best right now is 6. So every planar graph is a subgraph of a path times, where times is a strong product of some graph of three width at most 6. Okay, So for example, this planar graph here on the left is subgraph of this product, and this, or what this thing on the right is a strong product of this tree. For example, in this case, the tree width is 1, so this is graph H, and this is a path, so the planar graph is a subgraph of that. So what's the strong product? I'll do this very quickly in a kind of loose way. So if you have two graphs, A and B, so this is A, the one on the left, and this is B, here's how you get a strong product. So if this is A, you can take B copies of A and put them in kind of one under another. And then for each vertex of A, you have all of these copies of that vertex, and you put B on it. And you do that for every vertex of A. Okay, loosely, that's what it is, at least in this example. If that was all, you would get what is called Cartesian product. But we are here looking at the strong product, which has some extra edges, and extra edges are as follows. If you take any vertex now of this Cartesian product, so Cartesian product would be the black edges. So if you take the Cartesian product of these two graphs, and you take any vertex, and you look at an edge in A, and you look at an edge in B, they actually form a quadrilateral, like here on the top. And in addition to the 4 black edges that form quadrilateral that you already have, you would add 2 crossing edges. So in this case, the pink, and so basically you would have a complete graph on these 4 vertices. So this, if you add the cross edges, you now get a strong product. Okay, so that is a strong product of 2 graphs. So on the left-hand side here, we have a Cartesian product. If you add cross edges as well, you get a strong product, which is the one here on the right. If you only add the cross edges, you get something called a direct product. I'm just mentioning it in case you haven't seen these 3 definitions before. Okay, so what is this good for? This theorem that we proved. Let's see if it's good for stacks and queues. Okay, so imagine if you look, it turns out it's useful for lots of things, but let's now look at stacks and queues, and let's recall a little tool. The little tool tells you if you have a layering in between, you have a constant number of non-crossing graphs, we are in business. Okay, but this product of a path and a bounded tree width graph, it looks a little bit like a grid, where this little tool can be useful. So let's see. So we have this a product. Let me show you this picture again. So you have this product of a bounded tree width graph and a path. And this looks kind of like a grid. And imagine you have a good stack layout of this graph H, or a good queue layout of this graph H. So let's go back and see what can go wrong, or maybe nothing goes wrong. Okay, so we have these layers from the product. So imagine that on the top, I'm looking at a stack layout of graph H. So in each layer, I have a stack layout of graph H, or a queue layout of graph H. So remember, we had these 3 relationships of the edges. Okay, so let's see if we're going to be in trouble if we are looking at one stack layout where, so we're looking at edges colored the same color, and in a layer, so this is graph H, these 2 edges were disjoint. In the product, in addition to these 2 edges that were disjoint, we are going to have these 4 edges underneath. Okay, that's what we're going to have. But since these red edges are completely disjoint, we can color the edges here with 2 colors, such that in between the 2 layers, we have 2 coloring, and each coloring is crossing free. So then the little tool tells us that this is going to work for stack layouts. If I have a stack layout here, if I have a stack layout here, disjoint edges are not a problem. They give me 2 more color classes in between the layers. Okay, so disjoint edges are not a problem. if I had a Q layout and I had two edges that are crossing, in the product, I'm going to have all of these edges here. So this edge is going to give me these two parallel lines and a cross. This edge is going to give me these two parallel lines and a cross. Well, the way they laid out, and you can actually see it from the picture, we can color them with these new edges in between, we can color them with three colors. The green edges, they are all parallel edges. They are from times path parts. They are non-crossings. Then diagonals, these diagonals here in one direction, they can use another color. We're going to get a non-crossing graph. And the blue diagonals are also going to be non-crossing. Diagonals in the other direction from the cross will be non-crossing, and they give a non-crossing graph. So basically, for one Q here, we get three colors, three-colored non-crossing graph in between the layers. So that tells us immediately that if you had a QQ layout, if you used QQs, for each one of them, you're going to get extra 2 Qs for purple and blue and 1 for green. So you actually immediately get that if your graph H has bounded Q number, then product of H and a path has the original Q, plus 1 for the green parallel edges and plus a 2QN for the purple and blue edges. Let's look at the stack final relationship. If we have two nested edges, here's when we're really in trouble. Look what we get. From the times path, we get these green edges that look like that. Okay, and then we have the cross edges from a strong product. But now they're going, because this is an outside edge, cross edges of this resulting from this edge look like that. They end here, they go from top here to outside most here, from top here to outside most here. And then inner one are completely inside. So if you had one stack with n nested edges, that's allowed, they're not crossing. If you have one stack graph here, you will end up here with n pairwise crossing edges. So in between the layers, we get n pairwise crossing edges, but you can say, well, the n pairwise crossing edges, your tool tells us just do this, right? Yes, we can do that, but then the green edges, the green parallel edges of times product create n crossing free edges. So we cannot use the tool. In fact, if you want to get rid of n pairwise crossing edges, you have to completely change the order inside of this layer. We don't know how to do that. Okay, so what did we learn from this? I didn't really want to tell you this proof of the Q layouts. What I wanted to show you is that we found a tool that was useful for Q layouts and completely useless. So far, at least, we didn't find any way to use it for Q layouts. And this may think, or you may think, well, this is just a curiosity. Okay, you have a tool that doesn't work. But even this knowledge is useful for what we were trying to do, which is separate these two, and I'm going to get to that. All right, so let's summarize what we know. What we know is that these Q layouts, they are useful for Qs. We get, if you have a strong product of the two graph, and let's say one is a path, you're really in business. If this other graph has bounded Q number, you are done. Your product has a bounded Q number. And this actually answered that question that I mentioned for planar graphs, because we just learned that this theorem tells us that H for planar graphs is bounded tree width and Q number of bounded tree width graph is constant. So basically that's how this problem was answered. I don't want to go into that. But let's revisit the list of things we know. So it used to be that we knew much more about stack number, but thanks to this product structure theorem, which can be extended from planar graphs to many other graph families, we now in fact know much more about Qs than we do about stacks. So this was the list that I showed you earlier, what was known about bounded stack number. And this is a list, what we now know about bounded Q number. The list for bounded for the families of graphs that have bounded Q number is now much larger. So if we want to separate the two, if these two quantities are not the same, these two graph parameters are not the same from some graph family, maybe we can find a candidate here. So let's see what we have here. For example, it is known that stack number of one planar graph. One planar graphs are graphs that you can draw in a plane with at most one crossing per edge. The crossings are allowed, but there's only one per edge. You can extend the definition to k-planar graph, where you allow at most k edges, k crossings per edge. Well, we only know for one planar graphs that have bounded stack number. Already for two planar graphs, we don't know that. And this proof for one planar graph is 30 pages. Even that is not simple. Using product structure theorem, we already know that k-planar graphs have bounded Q number. In fact, everything for which you have a nice product structure, you have seen we have a bounded Q number. So what are the good candidates to separate these two classes? For example, you can say, I should look at some graph product that has bounded Q number that perhaps here doesn't have a bounded stack number. So that could be a good candidate to solve this problem. So let's try to cook that up. So what is the goal? The goal here is I'm going to try to crack this line. I'm going to try to show that there is a graph family that has a constant Q number, but unbounded stack number. Okay, so for that, first of all, I need to have a way to prove that some graph family has unbounded stack number, even unbounded Q number if my goal is to prove the other one. Okay, so the goal will be, I need to be able to prove that some graph family has an unbounded stack number. So far, until this work, the only tools we had for that was density. Remember, if you have more than linear number of edges, then your stack number, both stack number and Q numbers are unbounded, so that doesn't separate them, but that was a tool. You prove that the graph has more edges than it can. The only other tool we have was counting, that you prove, you look at a family of graphs, you count how many graphs there is in that family, and it turns out there is more graphs in that family than there is graphs of bounded stack number or bounded Q number. For example, that's how we show that graphs of bounded degree, not all the graphs of bounded degree have bounded stack numbers. So the tools that we had so far were counting and density. But now we have something else. We learned something from this product structure. So what did we learn? Okay, we're gonna try to use this new thing we learned. Well, new old, some of these things we knew before. Okay, so strong products are good for Qs. Let's try to use that. And they're not good. It seemed that they're not good for stacks. Okay, so let's summarize what was known about these strong products of Qs. In fact, David Wood already in 2004, he knew, or he proved that strong product is good for Qs. So what he proved is that if you have a Q layout, if you have a strong product of two graphs where H1 and H2, where both H1 and H2 have a constant Q number, and one of them has bounded degree, there's a bounded degree here. Oh, then the strong product itself, if all of this is a constant Q number of H1, Q number of H2, if delta is a constant, you get a constant Q number. Okay. He showed something stronger, of course, for Cartesian product, it has less edges, so he managed to get a better bound here. You don't have multiplication of Q number of H1 times Q number of H2. Let's see what was known about stack number. Our product's good for stack. We saw, at least in my example, that they didn't seem to be good, but some things were known. In particular, this was known. So let's just focus for a moment on Cartesian product. So here's what David proved in 2004 about Cartesian product. Already in 79, basically the same thing. So let's see. What was known for Cartesian product of Q number, you have that if the degree is bounded and both the Q number of H1 and H2 is bounded, you have a bounded Q number. Basically the same thing was known for stack number of a Cartesian product. Remember, Cartesian program doesn't have those problematic x's that I showed you. Okay, so they were problematic. In my bad example, the x's, the cross edges were crucial to create a bad example. And here is a Cartesian product. But even there, if you're looking just at a Cartesian product, there was a difference between the two statements. This was true only when the H2 was the graph of bounded degree was bipartite. So the one that has bounded degree also needed to be bipartite. If you have these two properties, then you get a bounded stack number of Cartesian products. So what would be the strategy here? And we really got to this strategy by studying product structures. It just turns out at the end, we were trying to use first strong product, but we realized at the end, oh, you can even do it without it. By using the difference here, the key is in this word bipartite. So if you want to find a graph family for which Q number is bounded, but stack number is not bounded, we need to pick H1 and H2, where H2 has bounded degree, we get a Q number. Okay, so you pick H1 and H2 such that the Q number of H1, Q number of H2 is bounded, such that the degree of H2 is bounded. And we also want to pick it such a way that hopefully stack number is not bounded of their Cartesian product. So if we, how we do that? So we pick H1 and H2 such that the Q number is bounded. But the strategy here is that we should pick H2 to be as far as possible from bipartite. Because otherwise, if it's kind of bipartite, then it's going to have a bounded stack number. So again, strategy, both H1 and H2 have bounded Q number, but H2, the one with bounded degree, we pick it such that it's as far as possible for bipartite. So we want a bounded degree graph that is as far as possible from bipartite. Here's something that is bounded degree and as far as possible as bipartite graph. It's a hex grid, okay? So it's basically hexagonal grid. And why do we say that? Why do I say that I claim it's as far as possible in some vague notion? It's actually notion is not very vague. I'll define it from bipartite. It's as far as possible in bipartite in the following sense. There is an old theorem by Nashvillians from 49 that says no matter how you color this n by n hexagonal grid, you're going to find a path from one side of the grid to another that uses one color, no matter how you color it with two colors. So for example, in this picture, here's this wide path, okay? And here, and I don't know. So I think I see only this one. Maybe there is more. But the point is no matter how you color this graph with two colors, you're actually going to get a component, a big component with linear number of vertices that have the same color. So you're really far from bipartite graph. So that is what we picked for H2. Okay, so we're going to take this H2 bounded degree far from bipartite. H1, we pick a star with n leaves. I don't want to go into that why. But if you take, so basically what then we know, this graph has bounded degree, has bounded Q number, even by the little example I showed you at the beginning. It's just a grid with little diagonals. This graph has a bounded Q number and bounded degree. This graph has bounded Q number, obviously, and the Cartesian product by David results has bounded Q number. And then with some ad hoc tools, we show that in fact, in Pigeonhole, Erdős-Zajkeres, I don't know, some ad hoc things, we prove that this graph has unbounded stack number. So we actually separated, at least in one direction, stack layouts and Q layouts by showing that there are graphs of bounded Q number and unbounded stack number. I think finally the stack number we get here is log n, or maybe it's double log n, doesn't matter. But this brings me to the following. So what did we learn? There's families of graphs that have Q number, in fact, 4 and unbounded stack number. That shows that stack number is not bounded by Q number. That also answers the question about whether stacks are more powerful than Qs. The answer is no. It's still possible that Qs are more powerful than stack. We don't know anything about the other direction. This construction also answered a couple of open problems from some other kind of related parameters. But let's see. So this is, I will show you how this was dramatically improved. Unfortunately, not the other one. Whether there are graphs that have bounded stack number, but unbounded Q number, it's still wide open. I'll repeat that at the end of open problems. But before I do, I'll show you how this result, unbounded stack number result, was improved. It's a wonderful result. So let's see what we knew. So we just learned that a Cartesian product, therefore strong product 2 times a hex grid has unbounded stack number. If you look at that graph, though, it has unbounded degree, okay, because it's times a star. Star has unbounded degree, so the product has unbounded degree. So we found the graphs of unbounded degree that have unbounded stack number and bounded Q number. Okay, what if we wanted a graph that has bounded degree? Okay, so here's, let's look what we've just, so what we proved there, remember the graph H in here is a hex grid. And hex grid is a subgraph of path times the path, strong product of path times the path. So we can rephrase this statement by saying that the stack number of a star times path is unbounded. Okay, so that's the same, it's completely rephrasing what we proved. And here we are putting a strong product. So we know already this is true, but this graph Sn star times P has unbounded degree. And then if you look at it, you think, well, if I replace a star by another path, I get a graph that looks kind of like a grid that has bounded degree, like a 3-dimensional grid. So the question is, can we replace this star by a path, okay, and still get unbounded stack number? The graph itself still has bounded Q number. Path times a path times a path has a bounded Q number because each of these graphs has a bounded Q number. So from the one of the products, one of the results on Q number on products, we know that Q number of this graph is bounded, but what about a stack number of this 3-dimensional grid? So this question was asked in Banff. Many people in the audience were there. This was last year. Last year in November or December, there were 15 people in the workshop in person and many online. And it was the first in-person workshop I went to after COVID. It was wonderful. But somebody asked these questions. I forgot who. It wasn't me. So somebody asked this question whether stack numbers unbounded of this graph, pi times a pi times a path, on this kind of a little bit more complex grid. And it turns out the answer is yes. It's not only that they proved, I'll show you the list of authors, not only that they proved that the stack number is unbounded, they found a tight bound and in fact polynomial bound for the stack number of such graphs. And actually, you already had a seminar about this. So one of the authors of this result is Sergey Norin, and he gave a full talk about this. So I'll just give you a 2-minute summary of what they proved and how the proof is beautiful. And they managed amazingly to get a tight bound. So they proved that the stack number of this 3-dimensional grid is n to the 1/3. Here on the picture, you have a path times a path of length 2, because otherwise it doesn't fit. So they proved that this graph has unbounded, in fact, n to the 1/3 stack number. It's actually the proof technique that is the most interesting here, and the fact that I managed to nail exactly the result. So how did they prove this? So they used the so-called topological overlap theorem of Gromov, like a big hammer. It's like a super strong result. They use a big hammer, but you have to know how to use this big hammer. And so to use it, first thing you have to show, so let me first tell you what was the graph, in fact, how you should view this now 3-dimensional graph. You should really view it in 3D. So the graph for which they proved unbounded stack number, you think of a normal three-dimensional grid, so the blue grid, and then in every face of size 4, so in these blue faces, you add just one edge. So in 3 dimension, you end up with kind of non-crossing graph with these triangular faces. So you have a so-called, so basically you get this two-dimensional simplex, okay, where these faces, you have triangular faces, they're not crossing. So you get, of course, in 2D, my drawing, that you have the crossings. So they start with that. And in order to use this Gromov's theorem, they have to prove that something called a bramble of this graph is high. In fact, so again, this is P times P times P. You have n to the 3 vertices in this graph. So in order to use this Gromov result, you need to show that this kind of 3-dimensional bramble is high, it's linear. I'm not going to go into what it is, but you think of it, these are that you have a collection of these triangular faces that have enough of connectivity to have a bramble of size n. Doesn't matter what it is. So let's say that set has n of these triangle. You have a set with n of this triangle that has a very specific property. So here's the property. Okay, I'm going to skip this because the main property is, don't look at any of this. So imagine that this graph here in the picture, that it has a stack layout with constant number of colors. Remember at one of the first slides, I said, oh, if you look at a stack layout, you have vertices on the line and non-crossing arcs. I said, you can take endpoints of this line and you close it off and you get a cycle. So saying that you have stack number K is the same as saying that you can draw, I'll end up finish in a minute or two. It's the same as saying that you can draw all the vertices of a graph on a cycle, and that you can draw all the edges inside of the cycle with straight lines, and you can color them with K colors, so stack number K, you can color them with K colors such that each color is non-crossing. So you have like a convex drawing, straight line, where the monochromatic edges are non-crossing. That's what it means. It's identical to saying that you have stack number K. So if this graph had a constant stack layout, it means that somehow from 3D, you squished, you found a way. Imagine that's possible. I can take this object, and if it's rubbery, I push it down on the plane such that the vertices are on a cycle, and such that the edges, I'll let them stretch, and the edges are in K non-crossing, how do you say that, formation, K non-crossing pages in the cycle. Okay, in other words, no K+1 edges are pairwise crossing. Okay, so I squish the whole thing into the plane, vertices on a cycle, and I can do that such that no K+1 vertices are pairwise crossing, because if I cannot do that, then no matter what I do, K+1 vertices are crossing, and therefore your stack number is not K. So what this Gromov theorem says, if you have this bramble high, in this case n, then no matter how you squish this object, this 3D grid, no matter how you squish it into the plane onto the cycle with vertices on a cycle, no matter how you do it, they will be n of these triangles. You see there are n of these triangular faces. There will be n of these triangular faces that have a point in common. Okay, so there will be n triangles that have a point in common. You think, okay, that's not exactly what we want, but basically it is. Let me just show you the last slide. Here's one of the triangles. When I'm trying to put down the next triangle, they have a point in common. So I cannot draw it over here, disjoint, because then they don't have. Indeed, I can draw n triangles inside of here that they're not cross. I just draw next one I draw here, next one I draw here is fine. But no, these n triangles have to have a point in common. So I start doing it, right? So I draw this edge, And okay, it's fine, of the next triangle. I said, okay, I don't want the next edge. I also don't want it to cross the green edge. Let's say I'm using 3 colors. I don't want green edge to cross this green thing. Then I have to do something like this. But then the red edges have to cross. And the point is really, I think if you play with this for 5-10 minutes, you will see that if you try to draw n triangles, you're going to end up with something like n over 20 pairwise crossing edges. So certainly, it doesn't have a stack number n. So you started with the graph that has n to the 3 vertices, and you show that no matter how you draw it on a circle, they will be n pairwise crossing edges. So you get your n to the 1/3 result. Okay, so that's the state of the art. And so finally, let's go back to what we know. We learned that indeed we can separate in one direction. There are graphs that have bounded Q number, but unbounded stack number. But in the other direction, it's wide open. We try, and not for the lack of trying, we tried. So far, we failed. So what we're missing is other graphs that have bounded stack number, but unbounded Q number. In fact, we don't even have good candidates. Well, I mean, you can cook up a specific graph of unbounded psi. You can hook up a special graph. But if you look into well-known graph classes, this one is a subgraph of a subset of this one. So in terms of B classes that we know, we don't have good candidates for the other direction. Let me add 2 more problems to that, which is do K planar graph. This is a very interesting one. Do K, for me at least, do K planar graphs with bounded stack number. We only know that it's true for K is equal to 1 by the result of a number of people. Related to that, is it true that a strong product of H and P, where P is a path and H is a graph of bounded trivet, do they have bounded stack number? If the answer is yes, then the answer to 1 is yes. I don't want to go into that. Why? I don't think we have an answer to this, even when H is a tree. So 3 times a path, does it have a bounded stack number? Even that we don't know. And here's the big one, is Q number bounded by stack number, the one I already mentioned. And as I said, we don't even have good candidates for that yet. Okay, I'll stop here. Thank you.